you to the Academy for this invitation to talk about some of the work that we have been doing. It's a program that we've been carrying out at NCRA for more than close to 2 decades now, and it's a real pleasure to be able to give you a status update on what has been going on. It's obviously, since it's been going on for a long time, there have been a large number of people who have contributed to this work. I'm giving this talk, but actually there are many, many players who've actually made all of this science possible. And here I'd particularly like to acknowledge the following 3 people, Apurva Bera and Aditya Chowdhury, who were PhD students at NCRA, and whose PhD work is by and large what I'm going to be talking about today. They really, I think they were some of the best students we've had at NCRA, and they've really done an amazing job. And also, of course, N Chengalur, who has been in many ways one of the driving forces behind all of the work that I'm going to be talking about today. So I'll talk about gas and galaxy evolution, and I do appreciate that the audience is largely not composed of astronomers. So I will give a fair amount of background about all of these words. I'll talk about gas, I'll talk about galaxies, I'll talk about evolution. So let me start, so there'll be a fair bit of background. Let me start first with evolution, where the question is the following, that we have only, of course, one universe. We are sitting here on the Earth. We can't do any experiments. We can only observe. We can only observe now, right? We don't have observations from, billions of years ago. We can't, we don't have those observations. But nonetheless, we are able to probe evolution, even though we are sitting here and making observations at one particular epoch. And that happens because light travels at a finite speed, which is something we are all familiar with, and so therefore objects are seen as they were in the past. So for example, we see the sun, as we all learned in high school, as it was about 8 minutes ago. The nearest star, we see it as it was about 4.5 years ago. And what I'm going to be talking about is galaxies, which are billions of light years away, so we see them as they were giga years ago. So therefore, even though we are not able to track a single galaxy over a cosmological era or cosmologically large amount of time, we are able to study populations. So we are able to study the populations of galaxies in the distant past. We are able to study populations of galaxies now, and that allows us to understand how the population is evolving. And that's more or less what I'm going to be talking about today. The other fact that you're all, of course, aware of is that the universe is expanding, and because of that, light from distant objects is observed at longer wavelengths than the wavelength it had which was emitted. So, for example, if I have a line from some particular element like calcium or so on, I know the wavelength of that light in the laboratory, but if that calcium line was coming from a distant galaxy, it would appear at a longer wavelength. And the ratio of the 2 wavelengths -1 is what is called the redshift. So the larger the redshift, the more expansion that has happened, and so the more distant an object you're looking at. So both distances and look-back time are basically parameterized in terms of this quantity called the redshift. And so, throughout my talk, whenever I'm talking about something which happened in the past or some object which is very far away, I'll probably use the parameter redshift to sort of characterize how far away it is or how much in the distant past we are observing it. Of course, the mapping between the redshift and the distance or the time depends on the history of expansion of the universe, or your model that you have for the cosmology of the universe. And so throughout this talk, I'll use something called the 737 cosmology to scale redshifts to distances and to look back time. All right, so that was about how we are able to study evolution. Let me just tell you a little bit about galaxies. Typically when you say a galaxy, what people imagine is a collection of stars, and that is indeed correct. A galaxy is by and large a collection of stars. For example, the Milky Way has, as some of you may again remember from school, about 100 billion stars. But that's not all there is to the galaxy. There are actually many, many more constituents. And one of the important constituents is dark matter. That is matter whose presence we infer because its gravity can be you can see the effects of its gravity, but you don't observe it at any electromagnetic wavelength or using any other tracer. but it has to be there because you can sort of see the effects of its gravity. So dark matter is a very important part of galaxies, and in fact it dominates over the normal baryonic matter of galaxies. There's a few times more dark matter in galaxies than there is baryonic matters. So the baryonic matter is like the tip of the iceberg. And in addition to the stars in the galaxy, you also have what is called the interstellar medium, that is the gas which lies between the stars, which is dominated by two different phases. The atomic phase, which in the astronomy jargon is called H1, this being the Roman numeral 1. And so I might slip into that jargon occasionally. So whenever I say H1, it means atomic hydrogen. And molecular hydrogen, which is called, is jargonized as H2. In addition, there are all kinds of other components in a galaxy. There's ionized gas in the disk of the galaxy, there's dust, there's cosmic rays, there's magnetic fields, and so on and so forth. But these, as far as the disk of the galaxy is concerned, are largely trace components. So, the bulk of the baryonic matter in galaxies consists of stars and atomic or molecular gas. And all of these constituents play quite an active role in the evolution of a galaxy. So if you want to understand how the galaxy is evolving, you need to sort of talk about all of these components and what they're doing. So as an example, I'm showing you over here an image made with the Giant Meter Wave Radio Telescope near the outskirts of Pune. I'll say a little bit about the telescope later on. But this is basically a map of the hydrogen in a pair of galaxies, actually a triplet of galaxies, where the red contours show you the intensity of the emission of the hydrogen gas, and the black is showing you where the starlight in the galaxies. So as you can see, the hydrogen extends to distances much, much larger than what you typically see in the stellar component. And in fact, there's a lot about this system of galaxies that you learn when you look at it in hydrogen, which you would not be able to infer if you were only working with the optical data that you have. So, this is one of the sort of standard sort of stories in astronomy, that if you look at things at only one wavelength, you end up learning only a limited amount about the object. You actually have to look at it in multiple different wavelengths in multiple different ways to fully understand what's going on. And that's basically the story over here, that we are trying to understand galaxy evolution, and so we'll have to put together observations at multiple different wavelengths to understand that. All right, so now let me continue talking about galaxies. So here let me sort of give you a cartoon picture of how galaxies are believed to form. You have, small perturbations in the density of the matter at some very, very distant epoch, and because gravity is attractive, the dense regions will sort of become denser, material will flow into it, and you'll have a kind of runaway process. Right? So the dark matters, the denser regions will go on becoming denser and denser, and the rarer regions will become rarer and rarer. And so this is driven completely by the dark matter, because it produces the dominant amount of gravity over there, and the baryons basically are just taken along for the ride. They cool and sort of collect at the center of the dark matter potential, and eventually the cold gas collapses to form stars. And the galaxies actually grow and evolve over time, and it's now believed that basically this grows in multiple ways. There's a hierarchical merger going on, that right at the beginning you have small objects and they continuously go on merging to form bigger and bigger objects. So the dark matter halos go on merging to form bigger and bigger dark matter halos. Each of the halos has a certain amount of baryons in it, and those also continue to sort of collate and form bigger and bigger sort of collection of baryons at the center of the dark matter halo. And in addition, the gas can actually be accreted from the intergalactic medium into these dark matter halos. And there are two possible mechanisms by which the gas could sort of flow into the dark matter halo. One is that it's sort of shock heated and it's sort of sitting around over there and then gradually cools and collects into the center of the galaxy. That's called hot accretion. Or there could be things called cooled flows, where the gas is actually originally cool, and filaments of the gas actually sort of flow in deep into the halo and start feeding the growth of galaxies. On which of these two is actually going to be dominant depends on many factors, but particularly the mass of the halo. So for the larger mass halos, typically as the gas falls in, it gets shock heated, and then you sort of have this hot gas around the galaxy which gradually cools and falls in. For smaller galaxies, you could have cool flows where the gas actually in filaments flows into the center of the galaxy. All right. As I said, to fully understand galaxy evolution, you have to put together observations at multiple wavelengths. And so, actually, a large amount of what we know about galaxy evolution has been gleaned from looking at optical surveys of galaxies. You study what's happening to the stars in the galaxies, because stars are the things which emit, which you typically see when you're doing optical astronomy. So, and it actually teaches you quite a lot about what's happening to these galaxies over cosmic time. And I'm going to show you over here, sort of summarize two things which are quite well established now. And those come from two parameters which you can determine if you have sufficient optical data. One of which is the stellar mass of the galaxies. So you're asking, in this galaxy, how much mass is there in stars at a given epoch? And the other is, what is the star formation rate at that epoch? That is, what is the rate at which the gas in that galaxy is forming stars? And it turns out these two things are quite tightly correlated. And I'm showing that to you over here. On the vertical axis is the star formation rate, each point being a galaxy. And on the horizontal axis is the stellar mass of that galaxy. And you can see that the two are actually correlated. And so the galaxies with larger stellar mass form stars at a larger rate. And so, and in fact, the bulk of the star formation in the universe happens in galaxies which lie along this sequence. It's called the main sequence. So this is basically the main sequence of star formation. This is the mode in which star formation typically happens in the universe, in which a mode in which the rate at which you form stars is proportional to the mass in stars that you have at that given epoch. Right, and so as I said, that's called the main sequence of star formation, and the bulk of the star formation in the universe happens in main sequence galaxies. We also know from optical observations that the main sequence evolves with redshift. This relationship depends on which epoch you look at, and that the amplitude increases with increasing redshift. By a very large factor, by a factor of almost 10 at redshifts between 0 and 1. So a redshift of 1 is about a billion years ago. So in a relatively short period of time, the galaxies have evolved very rapidly. The slope of the main sequence also evolves, but it evolves much less rapidly than the amplitude is shifting up and down. So here in these plots, what we are doing is basically we are sort of looking at individual galaxies and trying to understand how the parameters of the galaxies correlate with one another. And the particular parameters we looked at were the mass of the galaxy and the star formation rate in the galaxy. But we can try and ask a different kind of question. We could ask the question that if I take a unit volume of the universe, and I ask how much star formation is happening in this unit volume, how does that evolve over time? So that we would call sort of this average star formation rate of the universe. So you have a unit volume at some distant epoch, you have a unit volume at a more recent epoch, and you try and see, in these sort of unit volumes, what's the average star formation rate. And that's what's being plotted over here. So it's the average star formation rate per unit volume. So that's the star formation rate of all of the galaxies in that volume all added up together as a function of redshift or of look-back time over here, right? So if you look at it, you can see that the galaxies actually, the average star formation rate of the universe is evolving very, very rapidly. It sort of is peaked at these redshifts between 1 or 2, redshifts between about 8 and 10 billion years ago, and it drops very dramatically after that, right? And again, if you go back to very distant epochs, the star formation rate is again lower. And so the bulk of the star formation actually happens in this redshift interval. We have redshifts intervals between about 1 and 3. And if you look at galaxies today and you ask, typically when did they form the stars that we are observing today, about half of the total stellar mass in these galaxies is formed between redshifts of about 1 and 3. So that's called the epoch of galaxy assembly, or the cosmic noon, because that's really where much of the bulk of the galaxy, as far as the stars are concerned, was formed. And so the question we'd like to answer, particularly that's the one I'm going to try and address in the talk today, is what is happening over here? Why, after the star formation rate being so high over here, has it begun to fall? And it actually falls quite dramatically, falls by about a factor of 10 or so. And to do that, I'll sort of need to give you a sort of cartoon, a very simplified cartoon of how stars form in galaxies. So broadly speaking, atomic gas, H1, cools to form molecular gas in galaxies, H2. The molecular clouds cool further and then fragment and collapse into stars via gravitational instability. So that's just sort of this picture I'm showing you over here. You have hydrogen cooling to form a molecular gas cloud that fragments into small dense clouds, and that sort of compresses further to form stars. The stars, once they're formed, actually begin to inject a lot of energy back into the interstellar medium. There's feedback from the winds and late stages of stellar evolution. There's feedback from if there are massive black holes in the galaxy formed. There's a huge amount of feedback from that back into the interstellar medium. So this process is actually much more complex than I've drawn. There is actually feedback cycles operating over here, but to 0th order, basically this is what is happening, that hydrogen is cooling to molecular hydrogen and sort of collapsing to form stars. And so, if you want a full understanding of star formation in galaxies, you would need to understand all of these components, what's happening with the hydrogen, what's happening to the molecular gas, what's happening to the stars over there. And much of what I was talking to you about really was about these stars, about the star formation, the stellar mass of the galaxy, the star formation rate of the galaxy, and we really did not look a whole lot at these bits, which is which you'd really need to look at if you wanted to understand the whole process, because these are the raw materials out of which the star formation is happening. And particularly the atomic hydrogen H1 is the primary fuel which is driving this entire process. So that's really what I will focus on my talk. But before I get there, let me say a little bit about what we know about this intermediate phase, about molecular gas. Right? So molecular gas, because hydrogen is a symmetric molecule, it sort of doesn't emit a whole lot, and it's difficult to detect in interstellar space. So molecular gas is often sort of measured using emission from the CO molecule, which is closely correlated spatially and correlated with cold H2 gas. And there are sort of calibrations which allow you to convert your CO intensity into a total gas mass. That's one of the ways in which you could estimate the amount of molecular gas in the galaxy. Another way you could try and do it is to use dust emission. Dust emits radiation, typically because it's quite cool. It emits it in the infrared or in the sub-millimeter regime, far infrared or sub-millimeter regime. And you could, again, from calibrations, go from observations of the dust emission to the total amount of gas. These surveys actually, particularly the CO surveys, have limited sampling because it actually takes you quite a long time to detect CO in distant galaxies. The dust emission studies typically cover more, much larger sample, but it's actually a little bit more indirect, your conversion from dust emission to the total gas mass. But nonetheless, putting all of this together, people have a reasonable understanding of what is happening to the molecular gas content of the universe as a function of time or redshift. So here on the vertical axis is being shown the average molecular gas per unit volume of the universe, right? So that's basically you look at all of the galaxies in that volume and you measure how much hydrogen was there in each galaxy, atomic molecular hydrogen, you add it all up together, that gives you the density the density of the molecular gas in that volume. And that's what's being measured as a function of redshift using all these different techniques that I've put together. And so you can see, broadly speaking, it follows a similar trend to what we saw in the star formation rate, that the molecular gas content seems to peak at about redshifts of about 1 to 3, and it sort of declines sharply on both sides of that. So one way you could characterize this is by measuring something called the gas depletion time, which is defined as a very simple ratio. It's the ratio of the mass of a molecular gas to the star formation rate. So it's basically telling you, if you form stars at this rate, how much time will it take for you to deplete all of the gas that you have? In the time which is the ratio of these two, all of the molecular gas would have gone into stars, and your star formation would cut off in this very zeroth order model where we are ignoring feedback. So that's called the gas depletion time. And it turns out that if you put this plot together with the earlier plot which had shown you about the evolution of the star formation rate, you can actually match the two by saying that there's a fairly constant gas depletion time for the molecular gas of the order of somewhere between half and 1 giga-year. So that means that the molecular gas, once it's there at a fairly steady rate, is just getting converted into stars. That's how you could understand both the optical and the molecular gas data. That you have molecular gas in the galaxy, the molecular gas content of the galaxy is evolving, and because it's converting into stars at a steady rate, therefore the star formation rate of the galaxy is also evolving. So that makes a fairly coherent story, but we wanted to go one step further back and ask, now what's happening to the atomic hydrogen as a function of redshift, or a function of look-back time in the galaxy, right? So to get a complete understanding, as I've said over here, you need to know how the atomic gas also evolves. So that brings me in some way to the heart of this talk about observing atomic hydrogen in galaxies. As we all know, hydrogen consists of a proton and an electron, and both of them have spins, and these spins have two configurations. They could be aligned or anti-aligned, and these two configurations have different energy. And so the atom could transition from one level to the other, and that would be accompanied by either the emission or absorption of a photon. The energy difference is very, very small. It's only about 6 microelectron volts, or if you talk about it in terms of frequency or wavelength, it's a frequency of 1420 megahertz, or a wavelength of 21 centimeters, which falls into what we would call the radio regime of the electromagnetic spectrum. This, of course, is the lab frequency of the emission. If you are looking at more distant galaxies, they would be redshifted, so the observed wavelength would be longer. So instead of seeing the line at 21 centimeters, you would see it at longer and longer wavelengths, which of course makes it very well suited to a low frequency radio telescope like the Giant Meter Wave Radio Telescope, GMRT. All right, so let me just give you a couple of slides on the GMRT. It's an array of 30 antennas, each 45 meters in diameter. It's following a very novel, cost-effective antenna design, which was brought up by Professor Govind Swarup, who basically sort of was, I would say, the person who's really sort of envisaged and sort of built this telescope. It's spread over an area of about 25 kilometers, and it's located about 80 kilometers from Pune, built and operated by NCR TIFR. So it was commissioned more than 20 years ago, but very recently it's been upgraded to have state-of-the-art instrumentation, and I'll say a little bit about that also. And it is the most sensitive radio telescope in the world at many of its frequencies of operations. All right, so despite the fact it's one of the most sensitive radio telescope, it is still very, very difficult to detect H1 21 centimeter emission from distant galaxies, and that's because the line itself is intrinsically very weak. It's very difficult to detect this beyond the local universe using telescopes like the GMRT. And the largest redshifts at which this line has been detected in emission from a single galaxy is actually quite small. It's only about 0.36, whereas we've seen that most of the actions happening at redshifts between 1 and 3. Right? So, 0.36 doesn't get you far enough. And it takes you a long, long time. So, for example, one of the deepest observations aimed at detecting sort of individual galaxies, about 1,000 hours with a telescope called the WSRT, and it was, that's got you to redshifts about 0.2. Of course, more telescopes are coming online, and there are sort of newer surveys going on with all of these things which I've listed down over here, and those will certainly and are already beginning to teach us more about galaxies in the intermediate redshift range. But the fact is that it remains a small handful of things which are observed, and these are very, very, very difficult observations to make. So what we wanted to do was to try and make progress, without having to wait for the next generation of radio telescopes. So the fact that we exploit is, a radio telescope doesn't look at some one point of the universe at a time. It actually probes a volume of the universe at any given instant. And that volume contains a large number of galaxies. So even though you may not be able to detect an individual galaxy, you do have enough signal over there to detect the average H1 emission of the galaxies. Now, in many ways you could try and do that. The particular way we try and do it is by sort of aligning and stacking the spectrum together. And that requires you to know the 3D position of all the galaxies to be stacked. So you sort of know where in the sky the galaxy is, you know its redshift, and because you know its redshift, you can sort of move the emission line to the correct wavelength, and then sort of add up the emission lines from all of the galaxies, and that gives you enough signal to noise ratio to make a detection. Right? This requires you to know the redshift or the recession velocity of the galaxy to quite high accuracy. Typically to accuracies about 60 kilometers per second, and that you would get from some optical survey or something of galaxies. All right, so I'll just show you graphically how this thing works. So here are 3 galaxies which lie in your volume. There are different redshifts, so their spectral line and it comes there, and so on and so forth. And at this signal to noise ratio, you can't make any statement about whether there's a line there or not. But if you sort of move them all up and align them together, the signal will coherently add, the noise will not coherently add up, and so gradually you begin to build up signal to noise ratio, and you can see the line that you want. All right, so as I said, we've been doing this for quite some time. I'm just showing you a pilot survey that we had done more than 20 years ago to sort of demonstrate that all of this works, and it's sort of just shows you that even with a relatively modest number of galaxies and a small amount of observing time, you can actually begin to sort of understand how the gas content of galaxies which you're not able to individually detect. These observations were actually about galaxies in a nearby cluster, and the particular science that we were interested in over there. Clusters have a lot of hot ionized gas, which can strip gas from galaxies, strip atomic gas from galaxies, and so on and so forth, which fall into it. So that was the science we were trying to understand about what happens to the gas in galaxies when they fall into this very hot intra-cluster medium. But what we are interested in now is what happens to galaxies across a large period of time. And as I said, there's a program that has been going on at the GMRT for a long, long time. It started with what I would call the legacy GMRT, which actually had a relatively narrow bandwidth of 32 megahertz. So that means we could only observe a small slice of redshift of the universe, only a narrow range of epochs at a time. And so that meant we had very few galaxies in our volume at a given time. And because of that, we ended up with only at best with tentative detections of the stacked H1 signals, and I'm showing you one from a very early observations. And so even though, this is barely at about 3 sigma, the constraints that you get on the gas density of the universe, basically the same thing as I was talking to you about when I was talking about molecular gas density, except in this one is the atomic hydrogen gas density as a function of look-back time. This is our measurement over here. Even though our signal-to-noise ratio was modest, the fact was that the numbers we got were actually competitive with what could be obtained by any other means at that time. Nissim and his collaborators, this was at relatively modest redshifts of about 0.3 or so. Nissim and his collaborators were also trying to push a little further at about redshifts of 1, where again, with the legacy GMRT, with reasonable amounts of integration time, what you end up with is sort of upper limits on the H1 mass, so you don't actually end up with a signal. They did push much, much deeper with the legacy GMRT, and very recently they've actually been able to to sort of show that even the legacy GMRT, if you were able to invest large amounts of time on it, would actually allow you to make reasonable measurements of the atomic gas content of galaxies. But in between, what happened was that the GMRT got upgraded. As I said, there was the problem earlier where the bandwidth was only about 32 megahertz, which corresponds to really small bits of redshift. Redshift interval of 0.03 to redshift's interval of 0.3, depending on whether you're working between nearby redshifts of more or more distant redshifts like redshifts of 1. So that interval was very small, and that didn't give you a large number of galaxies. And the more galaxies you have, the better all of this works. So the upgrade of the GMRT changed the picture completely. The upgrade actually resulted in essentially a new telescope. I sometimes sort of say that everything excepting the steel and concrete were changed, but even that is actually not true, because in some places we even changed the steel and concrete. So we should really think of it as a new telescope. But the main thing which is relevant for us today is that it changed the bandwidth from 32 megahertz to 400 megahertz. So that's more than a factor of 10. And so that really increased the sensitivity of the telescope to observations of this type by a very, very large factor, by a factor of about square root of 10, which is quite large. So again, I'm just showing you the difference between the upgraded GMRT and the current GMRT. This is just, these small bands sort of show you where the earlier GMRT was able to observe. It could only observe in these small bands over here and over relatively small bandwidth intervals. The upgraded GMRT actually can observe this large pink region at a time, and the redshift interval that it can observe at one shot is actually quite significant. We're talking about redshift intervals from about 0.3 to 0.4. There are gaps in the coverage, but that was by design because there's terrestrial interference in those regions. So what I'll talk about today is basically observations at these two bands of the GMRT, which are called band 4 and band 5. I'll sort of end with my bit about the GMRT with this last plug on the telescope. So this is basically comparing the upgraded GMRT with other telescopes which exist. So this is sensitivity in some units on the vertical axis, frequency on the horizontal axis. The blue points is where the GMRT was before the upgrade. The pink points are where it is now. And the lower the points, the better the sensitivity. So you can see that these are more or less the lowest points on this plot if you exclude these, and these are for a telescope which has not yet been built, which is the SK, the Square Kilometer Array, which is expected to come up towards the end of this decade. So, and this is really thanks to Yashwant Gupta and all of the other people at the GMRT who've really plugged away to do the upgrade. We now have a very, very sensitive telescope to do these observations. All right, so we did, once the upgrade was over, we started on two redshift ranges, one on band 5, which is a more sort of local bit of the universe. So where we observed from redshifts of 0 to 0.4, but because you're actually observing a cone of the universe, the bulk of the observing volume is at larger redshifts. And the other set of observations that I'm going to talk about are between redshifts of 0.74 and 1.45, which are what we call the band 4 receivers. And these form the PhD thesis of Apurva Bera and Aditya Chowdhury. And so these observations yield two kinds of measurements. The measurements of the H1 spectral line, which is what we were primarily aiming at, so that we could measure the atomic hydrogen content of the galaxies. But it also allows you to measure the synchrotron continuum radiation from the galaxies. So I mentioned at the start that galaxies have cosmic rays in them. These cosmic rays sort of spiral around in the magnetic fields of the galaxies, and because of that you get synchrotron emission coming out, continuum radio emission coming out from the galaxies. And that is of great interest to radio astronomers, because it turns out that the intensity of the continuum emission is a direct measurement of the star formation rate. So if you can measure the synchrotron emission of the galaxy, you can estimate from your observations the rate at which the galaxy is forming stars at that epoch. Right? So from this one set of observations, we are able to measure both the atomic hydrogen content of the galaxies. We are also able to measure the star formation rate. Both of these are done by stacking, because the individual galaxies are too faint to detect. All right, so we needed observation fields where we had a large number of galaxies whose positions and redshifts, whose three-dimensional positions in the universe we knew. And so one of the sort of fields that we found best suited to our work was something called the Deep 2 survey, done with an instrument called DEMOS at the Keck telescope. And it was very suitable because the survey areas are actually, by and large, a reasonable match to the GMRT field of view. It has very, very dense redshift coverage. That means we get the measured redshifts for a large number of galaxies in that field of view. It has quite good accuracy, and it also has, a lot of ancillary data available, which allows us to make independent measurements of the stellar mass, the star formation rate, and so on and so forth. Right. So let me start with Apurva's work, which was for the lower redshift system. So he observed what's called the EGS field, which had a better redshift accuracy, about redshift of 0.3. And even though this was a redshift range that we had observed earlier with the GMRT, now that we had the upgraded GMRT, you have a factor of 5 larger sample than what you had for the old galaxy, for the old GMRT.
Jairam, you have 5 minutes.
Yeah, I'm doing okay. I'll get done by then. Thanks. Right. So as I said, the bulk of the observing volume is on the far end of the volume, so far end of that redshift space. So the median redshift of the galaxy sample is about 0.34, and when you stack things together, you have a very, very clear detection at about 7 sigma, and it's the first statistically significant measurement of the H1 content of star-forming galaxies about a redshift of 0.2. And what we were able to see right away is that there's already a fair amount of evolution in the H1 content of the galaxies. The galaxies are significantly more gas-rich than the galaxies in the current universe. From the same set of galaxies, you can actually measure, as I said, the radio continuum and get the star formation rate of the galaxies. And these also turned out to be one of the most sensitive observations made with the GMRT. So this is what the image you get when you stack the radio continuum. You make a very clear detection again. You can measure the gas depletion time of the atomic hydrogen just from our observations alone, the mass of the hydrogen to the star formation rate of the galaxies, and it gets to you about 9 gigayears, which is similar to the galaxies in our local universe. So it has a whole lot more gas, but it's depleting at a similar kind of rate than what you see over here. The data actually can be used for a large number of other studies, which we have been doing, but I won't talk about today. Instead, I'll just end by talking about the second survey done by Aditya Chaudhary at a larger redshift. These were basically samples which were selected originally to be at redshifts below 1.45, but above 0.7. So that really worked very well for us. It matches well to the band 4 receivers. It gives you a large number of galaxies with redshifts around 1. And so here's the result that we got from for our first pilot survey, just about 60 hours of observation. You make quite a convincing detection, 4.5 sigma. And so for the first time, you're actually able to make statements about the atomic gas in star-forming galaxies at redshifts of as large as 1. This is the image of the atomic hydrogen that you get if you stacked all of the galaxies together. That was the pilot observations. Aditya went on to get about 500 hours to sort of understand things in more detail. And so once you have much more sensitive observations, you're actually able to split the sample in different ways and understand how the gas content depends on different parameters. And here what I'm showing you on the upper plot is the H1 depletion time. That is the amount of time it'll take for the star formation rate to completely run through the hydrogen that you have as a function of stellar mass of the galaxy, if we split it into 2 bins. And you can see that the higher mass galaxies actually form stars at such a rapid rate that they simply run through the atomic hydrogen in very quick time. They run through the hydrogen in less than about a gigayear. Right? So in less than a gigayear, the gas would be completely consumed into stars for these high mass galaxies. And that's particularly interesting because it's these high mass galaxies which actually dominate the decline in the cosmic star formation rate. So basically, I've shown you that the cosmic star formation rate drops by a factor of 10 between redshifts of about 1 and redshifts of 0. And that drop is actually dominated by galaxies in this bin. So it's very interesting that these galaxies actually don't seem to have enough gas to sustain the star formation rate at this time for the period of time between now and redshifts of 1. It sort of gives you an idea as to why that decline is happening. And to sort of reinforce that is exactly the reason. What we did was we sort of split the galaxies now into two redshift intervals. One redshift interval right here, which is the peak of the cosmic star formation rate. The other redshift interval over here, which is where the star formation rate has already begun to fall. And what we find is that the average H1 mass of the galaxies actually falls quite sharply between here and here. Right? Between redshifts just above 1 and redshifts just below 1, the H1 mass of the galaxies actually falls by a factor of 3. So what it suggests basically is happening is that the galaxies are converting their gas into stars, but they're not able to accrete fresh gas fast enough in order to keep up for this sort of conversion of gas into stars. So it basically implies that insufficient gas accretion is the cause for the decline in the star formation rate. So I'll end up with the summary, which I won't read given the time, excepting maybe I'd like to say that there are many, many more things which came out of this survey about scaling relations, gas accretion rates, the mass function of galaxies, which I hope to get the chance to tell you at some future date. Thank you.
How do you estimate how far these galaxies or the stars are? Again, from the redshift?
Yes, from the redshift and the cosmological model for the expansion of the universe.
So everything you're estimating from the redshift, right?
Yes.
So how reliable or how precise this is, given that, say, hydrogen also you're estimating, the atomic hydrogen also you're estimating from the redshift?
Yeah. So the redshifts we don't get from our observations. The redshifts we take from the optical observations of the survey that we've sort of built all of this on. And over there, they have multiple checks on the reliability of the redshifts. For example, they may have multiple optical lines of different elements, etc. Or they might have observed the galaxy more than once to fold in instrumental errors and so on and so forth. And so that gives them a fairly robust estimate of the accuracy of the redshifts. And so, as I said, they're typically of the order of 60 kilometers per second or better, which is very good.
So very impressive work, Jairam. So I wanted to ask you, by the stacking technique, you get an average value for the hydrogen mass, solar mass, I guess, and same for the star formation rate. Yeah. So do the other people who also get a similar value? Using the optical surveys.
So we are the only people who've pushed out to these redshifts. So at the moment, there's nobody else to compare with. But there have been multiple studies of the stacking technique, etc., and so on and so forth at lower redshifts, where there's no indication that the measurements you get have any problems.
Why do you think there is a depletion of gas accretion at a higher redshift? Do you have any ideas?
Why does the gas accretion stop? I think it's stopping simply because the average density of the universe is falling and so on and so forth. So it's kind of a natural thing to happen.
I just have a novice's question. So you mentioned that observing the universe in different wavelengths is essential. So now we have this big new, all of us know about JWST.
Yes.
So what would be the special improvement that JWST will bring about in trying to address this?
Yeah. So the JWST works in the near infrared, and so it actually is also very good at many of the kind of observations that I was talking about. It may not quite do redshifts for as large a volume as you want, but it'll certainly allow one to push studies of galaxy evolution to much higher redshifts than were possible with ground-based studies, which is already happening.
That's so good. Yeah. You mentioned, I wanted to kind of have a comparison between these kinds of studies look at a large volume.
Yes.
But their sensitivity by definition is.
JWST will push to
a very high sensitivity, but it looks only at a very.
It looks at relatively smaller bits, but and its real strength is to push it to much higher redshifts.
But otherwise, because of these two effects, to the net result we will get sort of a comparable. I'm just
they're very complementary. I mean, the JWST gives you information that you could not get with ground-based facilities. So they are complementary. You should
Just
not.
because
Yeah.
they go much farther.
They're more sensitive. They go much to much. You can push all of this to much higher redshifts.
So even if the regions are small, it still gives you
They're
significant.
sufficiently large that you can actually learn quite a lot.